Now, in terms of the handshake, I know that you have an example of what that handshake looks like between SOLIDWORKS. Do you want to pull that up?
I do. So this is talking a little bit about the different product capabilities that we have for those tools. We will come back to that, but what we are going to talk about for that handshake is an example of a deep draw process. So for those of you that are unfamiliar, this is a sheet metal forming application. Effectively what happens is we have a sheet of, well, shiny material in this particular case, but we have a bottom piece of the die, we have a top piece of the die, so they clamp it together. Then we have an actuation that will push.
What makes this, maybe you have more on this, but what makes this complex? Like, why is this such a hard problem to solve?
So we are dealing with a isotropic material property, so that would, of everything else that we have just discussed, indicate that this is going to be an easy solve. But the big thing that's happening here is large-scale plastic deformation. That is to say, deformation of the part that is not something that's going to bounce back from. We're changing the fundamental shape and molecular alignment of the material, right? Like that's what we're doing. And as a result of that, we need something that's got a little more power to it. So the way that this process is going to work, and this is actually a little bit better of an application for it because this is the cutout piece of it. We have our die. This is the bottom portion of our die. That piece of material that we have, that sheet metal, that's our blank. That's the word for it. We have another piece that's going to hold things in place, and the tool that is actually making that big cut, the shape there, is called the punch. So the punch comes down and basically makes that face, but you have a die and a holder holding the blank in place. Then you have the punch come down. Then you have it come back up. So we actuate all of these things within the software itself. Now, the workflow itself is pretty straightforward. We can start in SOLIDWORKS with an initial design. After that, we need to do our scenario creation. And what I mean by that is we just set up how we want to run the simulation. So I need to tell the software those steps that I want to do and what everything is going to be in there. We can get an initial design from our results. We can bring it back into SOLIDWORKS for a design change if we want to, and then we can make our simulation run again. And all of that happens what we call the handshake, right? So we jump back and forth between our SOLIDWORKS tool and our simulation tool. Make sense?
Yeah.
Great. I will jump around a little bit of this if we need to, but I'll just hop in with the start here as well.
Awesome.
So let's take a look at how that handshake starts out. So we have our setup in here that should look very similar to what we just saw. And there's actually a couple of buttons right within our workflow here where we can export this out to the 3D Experience platform. I skipped the step here, but there's actually a little button that pops up in the bottom right-hand corner of the screen. You click that, you let it in here. So for those that are familiar with bringing files in or out or dealing with large assemblies in SOLIDWORKS, you should be familiar with that little green check mark. So that is indicating that we have uploaded this to our next platform here. Now, the interface is a little bit different, but that's basically how it works. So the next thing that we do once we have it uploaded is we have to specify what we're going to use for this role. So we're going to scroll on down to Structural Mechanics Engineer. We're going to go ahead and select that role, and then we need to specify what we want to do within that study. So in this particular case, we're going to create a structural model, right? So we can click that, and we can get to our next step here. And it pumps it in like this. So a couple of things have happened. This actually automatically creates a mesh, and we can kind of understand how everything's set up. Now, I haven't talked about what a mesh is, but just know it's the fundamental building block of a simulation. The purpose of a simulation is to take a big, real, complicated physics problem, break it down into bite-sized chunks so that our computer can process it. And those little squares and things like that, that's so it's easier to do those physics equations. So it'll automatically mesh it for you. It's one of the things that actually works really well within this tool. So
is that off of a, well, maybe you're just about to get to that. Is that off of a consistent, like is it looking at the part and it made that a shell model because it was a surface, or?
There's a little bit of smoke and mirrors that I did there, just full disclosure, but yeah, that's basically what you do.
Okay.
This is actually how we can select it. So when we are generating a mesh automatically, we can specify a couple of things that we want to kind of get in there. We have some controls that you can dive further into to make specific changes because we're in a high-end tool. But For the purposes of just getting this set up, you can just do basic settings to get this example to do what we want it to do.
Now I notice it does have an option for advanced there. Does that allow you to set up rules of how you want it to analyze the models and then generate mesh on a part-by-part basis?
It does. You got it right on the head there. That is a way to modify your part so that you can get this a little bit more in line with what you need. But for the purposes of what we did here, we did that for general purpose standard.
And that's just, you think back to that contact conversation. If you're getting into complex scenarios where you have a lot of parts and each of them need different mesh conditions and you're doing something somewhat similar but different and consistent, the amount of time that having a set of rules that it can just look at your model, understand what you did last time, and carry that out, that's a huge advantage as well.
Oh, yeah. And you can do all kinds of great things with this, which help to shorten that time that you actually need to get a part out, right? Yeah. We also do have a lot of complicated mesh rules that we can do in here. So with SolidWorks simulation, you're more traditionally limited with what you can actually run. If memory serves correctly, it is just it's tet meshing, surface meshing, that sort of thing. Yeah. For those of you that are interested, there's a lot more control that we can have in here and a lot more stuff that we can do. There's some very specific use cases for all of these. We do not have time to go into them, so we are going to jump right ahead.
The advantage of variety of mesh, good mesh equals better accuracy, or what's that breakdown?
Yeah, well, God, have I said it depends already? Because I feel like I should have. Okay. It depends. So different meshes have specific applications. So if I, for example, am trying to run a study on a plastic part, we'll do an injection molded part, right? That is traditionally done with more surface meshing because it's easier to get results there. It's a thin part. I don't want to have a lot of complexity because more complexity is going to cause me to have longer solve times if I'm trying to do a simulation on it, right? So that's kind of how these get set up. So more mesh diversity can make your part run more efficiently, but it doesn't necessarily mean better quality meshes. That is kind of a case-by-case thing. Again, the language of simulation. Yeah. So as we go through, we set this up. There's a few more things that we can go ahead and do. Basically, run our scenario, define what we're going to call it. We've already defined some context and things like that. And we're going to very on the nose name it deep draw. It's fine. But we have some options to pick right there. I can pick what type of study I want to do here. And because this is going to be a structural simulation, that is what we do. I can also do thermal, things like that, but it's not really applicable in this particular application. Once I go through, I can go ahead and run it and I can get my results accordingly.
Setting up the step itself, we're seeing explicit dynamic here, and that's that big differentiator in terms of complexity. Is that correct?
Yes, and you're going to be real excited because I have a slide that talks right about this too. So we are addressing what is a big factor in why you would need a higher end tool. We have our implicit versus our explicit, and there's a lot of ways that this can be defined, but there's some big terms that can be more readily associated with it. So when we talk about an implicit study, this is more akin to SolidWorks simulation. That can either be a static or a dynamic. So it's moving or it's not moving. If it's explicit, it's generally moving. The way that we do any kind of movement is generally with an implicit study. If there is movement, it happens slowly. And slowly is relative, but think faster than a car crash, and you're usually better with an implicit study. With an explicit study, it's extremely nonlinear and happens very fast. Again, a car crash is probably the gold standard of what would be an explicit dynamic study.
Phone dropping.
Yeah, phone dropping. That's a great one too. No, it depends on how far you drop it up, but I'm just kidding because the impact is the thing we care about. So it could be a large variance in like very few steps as opposed to a small number of things. Maybe you have a very small number of increments, that sort of thing. But the basic thought process is if it's moving fast and stuff is happening, explicit. And that's where you're going to need this higher end tool. If stuff's not moving so fast, you're probably okay with a less complex tool, depending on what you have. Again, it depends. But as a broad overarching category, that's sort of how we can set that up.
So with this differentiation. If you're looking at the explicit being something that's very fast, so car crash, the impact itself is very, very quick. But then like the wing failure, you want to see what's happening to the car parts and where they're going potentially. Let's say that.
Potentially.
That could take longer. That could be like seconds after the actual impact. Is there a second step added to that of a different type, or does that explicit carry on even if it's
I'm real sorry. I'm going to say it depends again. It depends. You could certainly make that all part of the same step. So in the car crash example, that scenario is generally over within like 4 seconds, right? Even with stuff flying around, like stuff that doesn't continue to fly. Maybe a hubcap's going to be rolling around, but like that's probably not going to hurt anybody. If I wanted to do another simulation after the fact, there are certainly ways I could take those explicit results and figure out what my deformation is from that impact, and then propagate that into a new study. That may be needlessly complicated, but that is something that you could do.
But an explicit study can extend multiple seconds. It can last seconds long.
It's just the term is that you have to converge the study, right? So like the more steps you add to it, the more simulations, the more equations you're going to be running is really what it is, which, of course, right? Okay. So after we set that up, we can go with our basically any other interactions that we want to have. There's some like general context that we can set up in this just so that we can make sure that everything is going to be touching appropriately. We can specify some boundary conditions, which is one of those things that we also want to do here. So I don't know if any of you have figured this out yet or not, but this is not the whole part. This is only a quarter of it. So what we are going to do is just specify some like symmetry constraints, assuming that what's going to happen here is going to happen on the other sides of the part, right? Again, the most important thing that we can do in a simulation is just make sure that the information that we provide to the simulation is as close to the real world, as accurate as we possibly can. So when we're applying our loads, when we're trying to figure out how we want to specify this out, we have to make sure that this matches as close to what we have in the real world as possible. And that's really what we're doing right here in specifying specific components and placing in all of our components. Also, if this is too in the weeds, we can certainly jump ahead to the fun parts with the results. But there's some pretty cool stuff that you can see in here as well.
In terms of getting started, people with SOLIDWORKS simulation, they're used to that interface. Mm-hmm. This is a bit of a different way of thinking. Instead of being in your left-hand side of your screen and working down, it's on the bottom of your screen and you're working left to right. But ultimately, it is still a bit of a flow, going through, setting it up, same general idea, but what's the best way for someone that's used to SOLIDWORKS simulation? Do you have any tips, tricks on a transition to a tool like the Simulia Advanced Simulation? Yeah.
So the language has already been learned at that point. So in a previous conversation that you and I had mentioned that simulation is a language. Having those fundamental building blocks and understanding exactly what is going on and why you're doing specific things is crucial to any of these processes. So if you have this fundamental understanding, you're going to be able to do this. You can probably fumble through and get some results. Some appropriate training is really the way to go because the languages have flair. Like I am from the Midwest, but I have a heck of a time trying to understand my friends in Alabama. So like it happens. It's a variance in accent is really the best way to think about it. You're speaking the same language, but you need to understand each other.
Yeah.
So that's how you would get around doing that. Just take some training. It's very helpful. But you shouldn't have any problem getting your head around what's going on. So one of the other things that I did want to talk about, and I had mentioned this previously, is that general contact tool. So instead of defining what surfaces are going to contact each other, I let the tool do it for me. It will recognize that anything can touch anything and basically do this with one check. So we can set that up pretty readily and figure out what's going to be there. You just need to activate it. You don't need to do anything else. That's it. It really does save a lot of time. Like I wasn't kidding. This is that same wire crimping example that I was talking about earlier. I can't say impossible to do in SOLIDWORKS Sim, but it is
hard.
Yeah.
To do accurately.
Exactly.
What about friction is that defined in the material that's applied to the part or the contact itself?
It is applied in the contact and the material, actually. So you can kind of
Do both.
Yeah. But that's sort of how this all gets set up. So a few other things that we can kind of take a look in here as well. Once we do our general contact, we can figure out all of the times that things connect, right? And it tells us what is connecting as we're stepping through this.
Now, when you say steps, compare that to SolidWorks simulation in terms of steps. What is a step in a simulation?
Oh, gosh. Well, so we are also talking about an explicit manufacturing process, which has stuff happening. So every single simulation I would run in SolidWorks simulation, I would have to run, we do up, we do down. Oh, no, we do clamp, up and down. So I'd have to do 3 separate simulations within SolidWorks simulation if I wanted to do something like this. So a step implies a simulation. I'm running a simulation at each one of these things. And the step is the step in the manufacturing process. So the first step is the clamp. So I clamp everything down. The next step is the punch. The third step is the removing of the punch. So that would be 3 separate pieces.
Yep.
Yeah. And when we run that, you can see where that kind of lines up. There's our lovely little part right here. And then we can look at our results. So the results that you would see here, they're not that much different from what you'd expect from any other simulation tool, right? If I'm looking at this from a structural component, I'm looking at things like von Mises stresses, factors of safety, things like that. Where it differs is that I do have access to some higher end things. Like I can run a destructive kind of simulation, right? I can see those sorts of simulations happening as I'm running through this. I can also activate and deactivate plots if I want to understand a better way my part's going to look here. But this is the interface. This is sort of how it looks. It gives you the option to explore in different ways. The different types of result plots that we see, they are all in the bottom left-hand corner of the screen there. So I'd mentioned von Mises, factor of safety. We could figure out thicknesses of specific parts. So like this one has been geared specifically toward a sheet metal forming example. So those are the types of results that I would want to see. I can figure out with my von Mises, I can figure out where I'm going to have some like issues potentially with tearing, and plastic strain are going to tell me that. Thickness is going to tell me if I will have any residual issues after the part is done. I want to make sure this thing is pretty uniform, right? Like that's sort of the goal of this application. But that's sort of how this is laid out.
Is there any differences of types of plots and results that you can pull from the Simulia versus SolidWorks simulation?
Yeah, you definitely get more diversity. So there's more things that you can do with the Simulia tools. You can learn a lot of the same information, but the information just has that much more like result file behind it, you know? Mm-hmm. And the rest of this is just a couple of little changes here too, but that is the gist of how the simulation is set up in this particular tool.
When you mention changes, you meant in SolidWorks, like you update the model. Is that what you're referring to?
Yeah. So with this particular one, I just made that blank way too big, right? So I know that, which means that if I want to continue this, what I would do is I would bring it back into SolidWorks and I just shrink it down. And this is a real simple part. So all you have to do is just kind of shorten that guy up, right? I'll just pick a different blank size.
Fully defined.
Yeah.
Good job.
Shrink it right down. So we bring it right back in. And then we can run that simulation again. And with a smaller part, we can see a lot less stress.
So you just had to click refresh. You didn't have to go through and apply the clamps, the forces, or anything.
Yep.
It just pulled the updated geometry in, had all of the setup remain. So when you're comparing, I mean, you're talking about somebody looking at this, they see it's a different interface in their experience with different interface of a simulation versus their CAD is that they have to export and then import and set up, and then as soon as there's a change, new file, import fresh file, or try and import an updated reference and have everything break. This is in a different interface, but very much so still connected to SolidWorks.
Yeah. The term we use is that you do not lose your parametric associativity. So everything that you do in SolidWorks, provided that you have all your proper little green check marks and things like that, you can bring it right back in. I didn't have to do anything else except just pull this right back in. the associativity from the SolidWorks model still remains the same. Like if I did something catastrophic, I would
Yeah.
obviously have to set some stuff up, but
Removed something that there was a reference to, or
yeah. And you could certainly like do that, but for the purposes of this, it was very straightforward. And you can absolutely keep it that straightforward as well. This is a simple example, but I can make more complicated parametric associativity so that I can make more complicated changes to my part.
What about the other way? Can it push?
Push geometry and things like that. So yes, it's a little more complicated, but you can certainly export those shapes. There's lots of ways to do it. A lot of people will export a mesh back over to SolidWorks and they'll model over it. That's a thing that people do. But yeah, you can absolutely do that.
And with this, you can even go beyond just running a simulation and parametric design studies and set certain standards and goals of ranges of this dimension can change within this range by this much. And my goal is to have reduced weight and still meet this strength and have it go through and run 10, 15, 20 simulations without you having to go in and manually change those. Can you, once you find that best outcome from those types of simulations, same thing, you can take that best outcome and drive that back into SolidWorks?
Yes, absolutely you can.
Awesome.
Yeah.